Let's look at solving optimization problems. The first thing we want to do is read the problem and introduce all of the variables and draw and label any figures as necessary. Next, we want to determine which quantity is being maximized or minimized. Then we need to write a formula that represents the quantity being maximized or minimized. Keep in mind that this equation often involves more than one variable. Using the same independent and dependent variables used to write the formula, we want to write equations so that we can write the quantity being maximized or minimized using a single variable. Next, we have to identify the domain of the function, keeping in mind that it also has to apply to the situation at hand. Finally, we locate the maximum or minimum value of the function we came up with. Note that this usually involves finding critical points or evaluating the function at endpoints. Let's look at a problem that involves minimizing the time it takes for someone to travel to a location across a lake. Here we have Jack at a point on the lake, and he wants to get across the lake to a point 4 miles south. Let's first draw a picture of the situation. Now we'll determine the time it takes him running and the time it takes him rowing. Recall that distance is equal to rate times time, so time is equal to distance over rate. Notice from the figure that Jack runs x miles, and he does so at a rate of 5 miles per hour according to the given information. So the time he spends running is equal to x over 5. Next, determine the time spent rowing. Jack goes y miles at 3 miles per hour, so t is equal to y over 3. The total time is equal to the sum of the time Jack spends running and the time he spends rowing. This is the equation we want to minimize. Let's find another equation from the given information that we want to use to write the equation for t using a single variable. Notice that a triangle is formed in the figure. We can find the length of y in terms of x using the Pythagorean theorem. So we get y squared equals the quantity 4 minus x all squared plus 2 squared. Then we take the square root of both sides to solve for y. Since we are talking about time, we can disregard the negative solution since y must be positive. Substituting this expression for y in t, we now have a function t of x. Notice from the figure that x can be greater than or equal to 0, and it must be less than or equal to 4. So that is the domain to be considered in this situation. The function t must be minimized at either endpoint of the interval or at one of the critical values. So let's find the derivative of t. The derivative of x over 5 is just 1/5. Then we have 1/2 times the quantity 4 minus x squared plus 4 all to the negative 1/2 all over 3. Then from the chain rule, we must multiply this by negative 2 times the quantity 4 minus x. Simplifying, we get 1/5 minus 4 minus x all over 3 times the square root of the quantity 4 minus x squared plus 4. The critical points occur when the derivative is equal to 0. So let's set it equal to 0 and isolate each term on opposite sides of the equation. Let's remove the fractions by cross-multiplying. That gives us the denominator that includes the square root on the left side, and then 5 times the quantity 4 minus x on the right side. Next, we'll remove the square root by squaring each side. By distributing the 9 through on the left side, then isolating the variable term, we are left with 16 times the quantity 4 minus x squared equals 36. Dividing both sides by 16 gives us 4 minus x squared equals 2.25. Then we take the square root of both sides, which gives us 4 minus x equals plus or minus 1.5. Solving for x, we get x is equal to 2.5 and 5.5. However, recall that the domain is from 0 to 4. Since 5.5 is not in the domain, it cannot be considered as a critical point. Note that it can be verified that 2.5 is the solution by substituting it into the equation and verifying that a true statement results. In this case, 2.5 does satisfy the equation. Now we have to test the endpoints and the critical point in t of x to determine which value results in the smallest value. If we substitute 0 for x, we get t is approximately equal to 1.49. If we substitute the critical point, 2.5, for x, we get t is approximately equal to 1.33. And if we substitute the other endpoint, 4, for x, we get t is approximately equal to 1.47. So, we know that the critical point minimizes t. But we are asked for the distance that Jack should run and the distance that he should row. We know x, so we need to find y. Recall that y is equal to the square root of the quantity 4 minus x squared plus 4. So let's substitute 2.5 for x. Evaluating, we get y is also equal to 2.5. Therefore, Jack should row 2.5 miles across the lake and then run 2.5 miles in order to reach the camp in the fastest amount of time.